Okay, hello, welcome to my channel. My name is Solo Anch, and in this video we're going to answer some questions from Reddit. Alright, so Reddit is a site where people go there to ask a lot of questions and some mathematical questions as well. So I found this question, and in fact there are going to be 3 of them, right? This one and 2 more, but I'm not going to do the 2 more in this video, right? We're going to do it in the subsequent videos. Good. So this relates really well to integrals. In fact, an application of a Calc 1 type integral. So yeah, so let's just see what we get. So to find the area of this green region, all right, which is enclosed by the part of this curve given as y equals to 4 over 2x plus 1. This line here, which is x equal to 0, and then the horizontal line here, which is y equals to 1/2. Okay, so this is a little bit different from just finding area under a curve, because here this horizontal line limits us. Okay, we don't go all the way to the x-axis, so we have to stop somewhere here, and we are going to tackle it this way. Well, we just find the area under this curve, ignoring the fact that this 1/2 is here. That is just going to find it all the way down to the x-axis. Then we are going to subtract the area of this rectangle from that in order to get the area of the green region. Okay, so we're going to look at this in the Riemann sense. So let's see. Well, we don't know, we don't have a special name for this curve, just like we have for a circle, for other plane shapes, right? Like a rectangle, a triangle, and others. So we don't have a particular formula for it. So what we do is to approximate the area under this curve by area of small rectangles. So this is what we'll do. So we can partition it this way, get this, get that. Let's put it here so that to be like we assume equal width. All right, now here I'm going to call this x1. We can call this point x0, x1, x2, x3, and so on and so forth. So let's just deal with an arbitrary partition point. Let's call this xi minus 1, and then this one will be xi, and then we can continue like that. Good. So let's see what we get. Well, we're going to extend this till we meet the curve, which we know the expression for it. Okay, so like I said, we are going to take the area under this curve, not minding this, but we're going to subtract the area of this rectangle from that. So let's see what we have. Let's put it this way. All right, you know that we are going to find the area. To find the area of this rectangle, we're going to multiply the base by the height, or you can say the length. So in this case, it appears to be like a height, right? So you see that from here to here, then we multiply it by the length from here to here. But we call this part xi minus 1 and then xi. So the area of this rectangle here will be the height, which is going to be the function y, all right, at some x in this interval. Let's say some x star. Then we multiply it by the width here, which is going to be xi minus 1. Okay, so this will give us the area of such a rectangle, this rectangle here. So maybe we can call it the height rectangle. But we need we need others. So if you take I will draw another rectangle here, draw this other one, and so on and so forth. You notice that with some all these rectangles, we're going to get approximately the area under this curve, y equals to 4 over 2x. So this is how I'm going to write it, that the area under the curve, so I'm going to use AC to denote that, all right? It's going to be the sum. Well, let's use this I, since it's just an arbitrary point, as our index, as our sum index. So that's going to be I starting from 1 up to n of them. We're going to multiply that. We're going to take the sum of, well, we'll take such. So that is going to be y, or evaluated as some x star. Now, I didn't tell you where this x star comes from. Well, x star is just any x in an arbitrary partition interval. Okay, so any x here, such that when you take the value to give you exactly this curve, that's what we mean by x star. Good. We multiply it by this change, which I can denote it by changing xi. Okay, so sorry, I didn't say equals to. It's supposed to be approximately equal to. Right? That will be the area under the curve. Good. Where this function here is known to be 4 over 2x plus 1. But this is just an approximation, because as you can see here, there is this space here is outside is not under the curve, is above the curve, which means it will not give us the exact, which means taking some of such rectangles will not give us the exact area which we need. but we can make it better by making the width here smaller. All right, you notice if we make the width here smaller, by that we'll get infinitely many rectangles to still fit in. The approximation will get better. So that means that we are going to take this, the area under this curve will become the exact thing when we take the limit as the number of partition points, which we call n here, tends to infinity of this sum, which we have already, the sum as I start from 1 up to n of this same thing you call y, which is given as that. So let's say y evaluated as sum x star, okay, then we multiply by the change in x I. Good. So that will be the area under the curve. And this right here, we can rewrite this using the integral sign as the integral of this function over the x variable as x changes from 0 up to 7 over 2. So that will be, that means that the area under the curve will be the integral as x changes from 0 up to 7 over 2 of, oh, that is far away. Sorry, let me clean it and put it down so you can see. That will be the, okay, the area under the curve will be given as the integral as x changes from 0 up to 7 halves of, okay, of this function right here, which is 4 over 2x plus 1, then we multiply it by, we are changing xi. So, like I said, as the number of partition tends to infinity, the width will be getting arbitrarily close, that is, will be getting arbitrarily small. In other words, the same thing we do with the derivative, the differential, the derivative, okay, the dx, we are going to put over here as dx. Okay, great. Okay, so let's see what we have. Well, this is the area under the curve, which will give us the area under this curve, not minding this line here, 1 over 2, which we say that to get the area of this region, we have to subtract the area of this rectangle from the area under this curve. All right, so what we'll do here is to get to the area, well, let's just get the area under this curve, then we'll subtract the area of the rectangle from that. So we just have to integrate this. Well, this is quite easy because we can use the fact that the derivative of the denominator can give us the numerator if we write the 4 as 2 times 2. So I'm going to write the 4 as 2 times 2 of this in this form. The 2 is here and then the 2, another 2 is outside, such that when we differentiate this denominator, we'll get the 2 at the top, which will just have the natural logarithm of the denominator. So this is going to be 2 times the natural logarithm of the denominator, which is 2x plus 1. And then we have to take this from 0 up to 7 over 2. Okay, great. So let's substitute and see what we have. When we substitute x to be 7 halves, this will just be 2 times 7 halves, which is 7 plus 1. That is 8. So that will be 2 times the natural logarithm of 8. Then we are going to subtract. We substitute 0 for x. So we substitute 0 for x, 2 times 0 will be 0. That will be natural logarithm of 1. Of course, that's just 0. So this is what we get as the area under the curve. So let me put it down here that the area under the curve is 2 times the natural logarithm of 8. Okay, so to get the actual thing, the area of this green region, that is the area of that R, we need to subtract the area of this rectangle from that. So let me just put it out here that the area of the rectangle, which let me use small rectangle to denote, the area of the rectangle will be, well, that will be the length times the breadth, or you can call height if you want. So the length times the breadth is going to be, well, the length here is 0 to 7 halves, that is 7 over 2, times the breadth, which is 0 to 1 half, that is 1 over 2. Well, that just gives us 7 over 4. That is the area of the rectangle, and this is the area under the curve. So to get the area of the green region, let me say the area of the green region, that is the region which we call R, is going to be, we subtract this from that, that will be 2 natural logarithm of 8 minus 7 over 4. Good, this is very good, right? But the question demands that we put our answer, or we put our area in this form, in the form b, then the natural logarithm of 2 minus, is it a? Yeah, this part is a. Okay, natural logarithm of 2 minus b. That is how the area is to be presented, okay, so that we can get our constants a and b. So how do we rewrite this such that we have natural logarithm of 2 right here? Well, we can rewrite it as 2 by rewriting it as 2 to the power of 3, all right? So by doing that, this is going to be 2 times natural logarithm of, in place of a, we're going to put 2 to the power of 3, and then we subtract 7 over 4 from that. So you notice by some logarithmic rules, we can put these 3 out front. So this is going to become 6 times the natural logarithm of 2 minus 7 over 4 as the area of the green region. Okay, so we put it in that form. So we notice that by that, A is going to be 6 and then B is going to be 7 over 4. And that's very nice, isn't it? Okay, well, maybe check. I didn't really check the form. Whether if this is plus B in the picture, it means the B here is going to be negative 7 over 4. But if this is minus B in the picture, it means the B will just be 7 over 4. So you confirm that. I'm going to check anyway. Okay, so that's it. Just by to find the area on that, you can just do that and you get it done, right? Okay, thanks for watching. And in our next video, we're going to do the other ones.